Hi everyone, I'm Greg Stitt, and in this video I'll be continuing with the FPGA timing optimization tutorial using a simple timer example. If you haven't already watched the earlier videos, I'd recommend going back and watching them first, because in this talk we're going to build on top of those previous concepts by performing timing optimization of a simple timer circuit in Quartus. And like before, the code that we will be optimizing is provided at the URL shown on the slide. So before we get into the optimization of this timer, I'll briefly explain the functionality that we will be working with. The corresponding system Verilog module is shown at the bottom right of the slide, where in addition to the clock and reset signals, the timer also has a go input that is used to start the timer, along with a cycles input that specifies the number of cycles to count. The timer also has a single output called done that is asserted by the timer after the specified number of cycles have elapsed after the assertion of the go signal. And in addition, the module also uses a width parameter to support different bit widths for the cycles input. This slide gives a brief overview of the functionality of the timer that we'll be optimizing. And if you want more details, you can look at the provided code to see exactly how it is implemented. So upon reset, the timer starts in an idle state where it remains until the go input is asserted by the user, at which point the timer then moves into the working state on the next cycle. In the working state, the timer will count once per cycle and continues to do this until the count reaches the requested number of cycles. At that point, the timer will assert done and return to the idle state. Now, the actual implementation of the circuit is slightly different. For example, the circuit stores the cycles input into an internal register when go is asserted. This is generally a good design practice because it protects the internal functionality of the timer from changes on the cycles input when the timer has already started. Similarly, the code uses slightly different names than what is shown on the slide, which are omitted here for simplicity. So one naming convention to be aware of is that some of the internal registers you will see use an _r suffix to make it explicit that the corresponding variable is intended to be synthesized as a register. So this slide illustrates a simplified look at the corresponding RTL structure of the synthesized timer circuit. Now this schematic omits many of the details on purpose because the intent here is to be able to illustrate the bottleneck that we are about to discover when we run timing analysis in Quartus. As you can see in the figure, the count register has a mux input that either allows it to be initialized to 1 at the beginning of the execution, or to add 1 to the previous value in the case that we are counting. The select for this mux, which isn't shown, is determined based on the current state and the go input. And as mentioned earlier, the cycles input gets stored into an internal register when go is asserted in the idle state. Now, one key part of the circuit is the comparator, which determines when the count has reached the specified number of cycles. And the output of this comparator affects both the next state and the enable for the count register. All right, so let's jump into Quartus and take a look at where the timing bottleneck occurs for this current architecture. All right, so here we are in Quartus looking at the compiled timer example. Now, before we get into the details, let's take a look at how I set up this project. So it uses virtual pins on the I/O just like the previous project did. And also, it is using a clock constraint set to 200 megahertz. So we want to make sure this can compile at 200 megahertz, and we will notice that it doesn't. So basically, if you look at this slow high temperature model here, the maximum clock frequency that Quartus was able to achieve was only 192 megahertz. And the corresponding setup violation, or the setup slack, was negative 0.2 nanoseconds. And the total negative slack was negative 3.2 nanoseconds. So it's not too bad, but we still have work left to do. So let's open up the timing analyzer and see if we can spot what the bottleneck is. All right, so here we have our failing clock constraint. I'm going to report the timing just like I did before. I'm going to accept all the defaults because we don't need to look past more than 10 paths. I'll report the timing, and you'll see that the top 10 failing paths all look very similar. They're basically going from the count register and ending at the count register. So all of them do that just with different pairs of flip-flops within that register. So the good news is that probably means that the bottleneck is the same for all of them. So if we optimize one, we will probably have optimized them all. So I won't go over the details down here again because you should know how this works now. But again, we see there's a little bit of negative slack right here that we need to optimize. If we look at the data path along the data arrival path, we'll basically see, equals, a whole bunch of equals logic, which is adding a fair amount to the logic delays. And if we go to the statistics, we see that the data portion of the arrival path, the logic delays are right here, the cell delays, are 41% of the total delay. So actually, the cell delays are not the biggest bottleneck here. The interconnect is 54% of the total bottleneck. But still, we want to try to optimize the logic for a very specific purpose here. So we're still going to look at optimizing the logic. So let's go ahead and take a look at what this critical path looks like in the technology map viewer and see if we can spot the issue. All right, so here we have, this is basically our source. It's one of the flip-flops of the count register. It's going through a lookup table, which is clearly doing some kind of equals logic. That wraps around to another lookup table that is also doing more equals logic, which then feeds another lookup table, which is doing more equals logic, which is then basically feeding another lookup table that's doing something to determine the next value of the count register. So really, the biggest bottleneck we see here in terms of logic is that our signal is having to pass through 3 separate lookup tables just to implement this equals comparison, which was the comparator back in our original code, or in our original architecture that we looked at. So this is the bottleneck that we need to optimize. All right, so as we just saw in Cordis, the comparator in our timer is causing a significant timing bottleneck. And the reason for this bottleneck is that the comparator has 2 times width total inputs, which created a deep lookup table hierarchy that required the count to pass through 3 lookup tables. So we now know that we have to optimize this comparator to meet our timing constraint. One possible option is to use pipelining again, like we did in the earlier example, but that would be a little challenging here because the increased latency could potentially break the timer functionality if we weren't careful. So instead, we're going to look at a different type of optimization, and we are going to try to reduce the number of logic inputs to the comparator to reduce the depth of the lookup table hierarchy. So how do we go about doing this? Well, one trick that can sometimes be used is to replace inputs with constants. So it might not be obvious how to do this here, but what we can do is use a different strategy where instead of counting from 1 up to the number of cycles, we can count from the number of cycles down to 1. And the corresponding circuit that uses this strategy is shown at the bottom of the slide. Now, if you look at the updated comparator, you'll see that the number of inputs has been reduced from 2 times width bits down to just width bits. This works because constants are not counted as logic inputs due to the way that lookup tables implement logic. So by reducing the inputs synthesis can now implement the comparator in fewer lookup tables, which reduces the logic delays that we saw originally. Now, one potential drawback to this approach is that we don't get to reduce the comparator inputs for free. What we are really doing is reducing the comparator inputs at the expense of increased inputs to the mux, because the mux previously had a constant input that has now been replaced by a non-constant number of cycles. Fortunately, in this example, the mux is not on the critical path. So in general, the strategy won't always work, but it does for this example because what we're essentially doing is stealing slack from a non-critical path to reduce logic delays on the critical path. Now, this optimization doesn't work when you basically steal slack from a path, which then essentially makes that path the new critical path. But that is not the case for this timer example, as we're about to see. So let's jump into Quartus and see how things have improved. All right, so now we're back in Quartus, looking at the optimized version of the timer. Now, I'm not going to go over the code for this because that has already been provided to you in the GitHub repository. So what we're going to do is just look at the timing results now and see if things have improved and if our constraints have been met. So I've already compiled this, and basically if I go to clocks here, we still have the same clock constraint we had before. We're trying to achieve a 200 megahertz clock. We see that all three of these models now meet our timing constraint. So if we look at the Fmax of kind of this worst case model here, the slow high temperature model, we see a clock frequency now that is significantly improved from the unoptimized version. So we are now achieving an Fmax of 217 megahertz, which is significantly above our constraint of 200 megahertz. And if we open up the timing analyzer, we can basically see that the bottleneck that we optimized away, the lookup tables that were being used by the comparator, are now going to be a lesser portion of the total logic delay. All right, so that's no longer red because we have no failing paths. We're still going to report timing to get the 10 most paths, the 10 paths with the least amount of slack, which is still the same path. But now down here we see it's meeting timing constraints. So now what we can do is take a look at the technology map viewer again. And now you will see it still looks similar to what it did before. It's passing through a lookup table that has to do with the comparator, saying equal, another lookup table that has to do with the comparator, and then the same next count logic that we saw before. But the key difference is, last time we did this, we had 3 of these lookup tables that were being used for the comparator. Now we only have 2. So we were able to remove the logic delay of 1 lookup table by performing the optimization that we saw in the slides, which was enough to meet our timing constraint. So we reduced our critical path so that it now runs faster than 200 megahertz. So the key thing to remember, or the main point of this entire example, is that whenever possible, you should try to find situations where you can replace a non-constant input to a logic resource with a constant. So it won't always work like we are seeing here, but it is a very useful strategy when it does work. So one other thing I'd like to point out is that you can actually optimize this timer a lot more than what we just did. So this will be posted as a future example, but I want to leave it to you for now as an exercise to see if you can figure out what other optimizations you could do to improve the clock frequency even further. All right, thank you for watching.